Hey there. Week two. We're starting off looking at a review of chapter 8, which is going to deal with work, power, and energy. Just finished up going over chapter 7 with momentum. Some of our objectives we're going to follow in this video lesson, and this week's lesson is going to be being able to define and describe work and power, which is obviously a major part of this chapter. We look at potential and kinetic energy and how work, power, energy, and all of it is related. I want you to be able to evaluate problems, calculate and evaluate problems with any of them. So in order to do that, you're going to have to know a formula. And I know some of the homework that you have is going to be doing problems. And then last of all, I'll look at how the work energy theorem, how it's all kind of interrelated and how you can use all of it. So work, basically with work, it's force times distance. We kind of talk about work in society as being different than what it is scientifically. I say I go to work. I'm doing a lot of work holding this thing. In science, though, it is specifically defined to be a force times a distance. You have to exert a force, and it has to move a distance in the direction of the force. And that's what's confusing for a lot of things. I say I go to work. I'm not really exerting a ton of force in moving something a distance. So this would be obviously more for those that are lifting weights, something like that. Yeah, you're doing work because you're exerting a force in the same distance. So it is obviously doing work. Now, I might get mentally tired, but I'm not doing work scientifically. So work has to be a force times a distance. And we could get into vectors, say what is the net force acting in that same direction that the distance moves. But it's still work equal to force times distance. With work, a couple of things we talk about because it's straightforward. It's a force times a distance. If I exert twice the force, I do twice the work. If I use the same force but I move it twice as far, I do twice the work. We look at work is very scientifically, it's very specific. If I hold something for a long period of time, I do no work. I do work in lifting that barbell or the weights up, but as soon as I have to just hold it there, I might get super tired, but I'm doing no work scientifically. The unit we're going to use, if I was to use a Newton of force and move in a meter, it's called a joule. I love the book in that one because it says rhymes with cool. So joule is something that is a very small unit of work. It's not very big. So most of the time, if we're talking about how much work is being done, we're going to talk about it in megajoules, kilojoules, something that is much larger than just one joule. Remember a physics professor I had in college one time basically said that if you were standing up and you were to take from the desk, a Big Mac from the desk to your mouth. That's about a meter, and that's about what a Newton of force would be. So relatively small when you look at it. They're saying lifting an apple over your head. It's not a lot. Joule is really small. When we look at power, basically, power is how fast you do something. So if I'm walking up the stairs like we did in one of our labs, as far as we walking or running up the stairs, you're going to be more tired running up the stairs than you are walking. But the difference is you're going to do the same amount of work. The work stays the same. It's the power is how fast it works. So it's basically, again, another one. It's work divided by time. We're going to use a joule for our work divided by a second. That's called a watt. And we're used to hearing kilowatts, megawatts. Again, a relatively small unit of power is 1 watt. But when you talk about kilowatts, you start getting into a larger unit that we would use every day. Kilowatts be used in not only power that you're doing lifting stuff, but it could be used in electrical power as far as the energy that's being used.